Hi everybody. In this little mini lecture, we are going to talk about balancing chemical reactions. So remember that all around us, chemical reactions are always happening, and we can't actually see those atoms break their bonds, rearrange, and come together to make new bonds in these reactions. We're just seeing macroscopic observations that chemical reactions are happening. However, what we can do is we can take those reactions and we can put them onto paper to say, hey, here's the reactants that we have, our original matter, and here's the products we're going to make at the end of it in terms of their chemical formulas. Then we also have to tell people, but we're not breaking the laws of nature. We're not breaking the laws of science. It all still does obey the law of conservation of mass and matter. So that's where balancing reactions comes in. It's taking these reaction equations for reactions that are actually happening, and it's translating them onto paper and showing how they react, essentially, what products they're going to form, and how it obeys law of conservation. So to balance reactions, we have to prove that all of the atoms that we had before are present after the reaction. They might just be rearranged and be in a different form, because that's the definition of a chemical reaction. You're making new stuff. So there's two kind of methods that you can use to help you balance a chemical reaction. One of them is a particulate diagram, and the other one is a table of values. Particulate diagrams are kind of helpful when you're dealing with simpler reactions, but the table of values is significantly more helpful when you're dealing with more complex reactions, and that one just kind of always works. So we're going to walk through both of them. So in this first example here, you can see you have methane, that's CH4, reacting with elemental oxygen to produce carbon dioxide and water. So this is an example of a combustion reaction. First method we're going to use is the particulate diagram method. So step one to drawing a particulate diagram is you have to kind of draw one of each reacting species and one of each product species that you have present to just kind of get a feel for how many atoms you have present. So if I start with CH4, I have one C, and that's bonded to 4 H's. I'm going to kind of set this up like a Lewis structure with my C in the middle and my 4 H's bonded to it. So in this diagram, you can clearly see that all of these circles here are touching. What that means is you're representing all of these atoms are chemically bonded. By representing them as touching, they're bonded together. Then I go to O2, so I'm adding O2 to it. O2 is one of our diatomics. It's a Hofbrinkel, so in its elemental form, it exists as 2 oxygens that are chemically bonded together, just like that. Then these two things are going to react together to make carbon dioxide, CO2. So I'm going to draw that out like this. And they're also making water. So it bothers me a little bit that my hydrogens are so much bigger than my oxygen, even though it doesn't actually matter really for this diagram. So there's my little model for water. Okay. So now what we have to figure out is how can we add things to it to get it to balance. So remember, if you're balancing a chemical equation, you can't just add things in wherever you want. You can only add the species that are present in your reaction, which means if I take a look at this, I can clearly see that I have 4 hydrogens on my reactant side, 3, 4, and only 2 on my product side. So in order to balance it, I can't just take hydrogens and throw them over here and say, ooh, now my hydrogens are balanced. It doesn't work like that. You can only add things in that are actually participating in the reaction, which means I can only add methane, oxygen, carbon dioxide, and water, because those are my reactants and my products. So if I want to fix the amount of hydrogens I have present, I have to add in more entire molecules to this equation. So if I have methane, which has 4 hydrogens, I know I need to add 2 more hydrogens to get that thing to balance. Lucky for us, water has 2 hydrogens in it, and it's the only hydrogen I have present in the reaction. So if I take this and I double it, I now have my 4 hydrogens that I need to get everything to balance. Let's take a look at the next element. So I've got carbon in here. I've got 1 carbon in the reactant side and 1 carbon on the product side. Nice, those are balanced, cool, don't have to do anything for those. Now let's take a look at oxygen. For oxygen, I have 2 oxygens on the left in the form of the diatomic. I've got 1, 2, 3, 4 oxygens on the right-hand side, the product side, and they're in different places, but that's okay. We're just really concerned about the number of atoms we've got. So if I have 2 oxygens on the reactant side and I need there to be 4, nice thing about diatomic oxygen is it comes in pairs. So if I add another one of those oxygens in, now I've got all 4 needed to balance this reaction. So if I counted them all up correctly, which I did because we already checked, this is now a balanced chemical equation. All the atoms that I had on the reactant side are present on the product side. So to take this, we now translate it to the chemical reaction equation by counting up the number of each particle that we used. So for methane, 1 methane itself has 1 carbon bonded to 4 hydrogens. And I only used 1 of them in this chemical formula, which means that in the formula equation, it would get a coefficient of 1. Remember that ones are something you don't always need to include, so you could just leave this off and just say CH4, knowing that there is 1 molecule, but I'm going to write it in just to make it super duper clear. Then for oxygen, I have 1 oxygen molecule that's made up of 2 bonded oxygens, but I used 2 of them to get this reaction to balance, which means I put a coefficient of 2 here. So I'm just counting up how many particles of each that I used, and I'm putting them in as coefficients. Next, you have CO2. I only used 1 of those, and then for H2O, I used 2 of those. So remember, our coefficients tell us how many of the particles that we have, whereas something like a subscript within that chemical formula tells you the number of atoms that you have, and they're bonded together. So you never want to draw your particulate diagrams with something like that, where all of those atoms are going to be touching, because that's going to indicate the formula for this would actually be O2H4. Everything would be bonded, and that's not what we're making. That's not one of our products. So if you're doing the particulate diagram method, make it super obvious what's bonded and what's not. If I do this exact formula or this exact reaction again, to balance it, I can use a different method. I can use a table of values method. So I'm going to show you that one as well. So to construct your table of values methods, what you do is you take a look at everything that's participating in this reaction, each element, and you make yourself a table of values for that element. So I've got C's, I've got H's, and I've got O's, and that's all I've got in this reaction. I'm going to write myself a little table down the center, and basically what I'm doing is I'm splitting this reaction into the products and to the reactants. Next up, I'm going to count up how many of each atom that I have. So I've got 1 carbon on the left, and I've got 1 carbon on the right. I've got 4 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, and 3 oxygens on the right here. Okay, now we take a look at what's not balanced. Carbons are looking okay for right now, so let's do hydrogens. For this method, what you want to do is you want to basically change your coefficients. You're manipulating coefficients till you get everything to balance. And if we think about a coefficient, what is it really telling us? It tells you the number of particles that you have. But let's say I gave you something like this, 3Mg3N2. How many atoms of Mg would you have? How many atoms of N would you have? Hopefully you said, well, there's 9 atoms of magnesium present and there's 6 atoms of nitrogen present. And that's exactly right, because to get those values, you take your coefficient and you multiply it by the number of atoms. So we're kind of going to make use of that process here, keeping in mind that coefficients mean you have entire particles, but to get the total number of atoms present, you still would multiply by any subscripts. So if I'm taking a look at the hydrogen only shows up in the form of H2O in this chemical reaction. So what I can do is I can figure out what number do I need to multiply by 2 to get the number that I want, which is 4, because between 4 and 2, 4 is the least common multiple. So for that, I would need to put a 2 in here. 2 times 2 gives me 4. So what does this 2 represent? Well, this 2 represents the number of particles that I would need to add in to get to a total atom count for hydrogen of 4. Means it's the coefficient. So whatever number you multiply that by, you immediately go up and add as a coefficient in front of the place where that atom appears on that side of the reaction equation. So to break that down again, I need to multiply hydrogen by 2. I'm doing that only on the product side of my reaction equation, which means that I'm taking a coefficient of 2 and putting it in front of water because water is where my hydrogen appears in the reaction equation. But if I put a 2 in front of hydrogen, that also affects the oxygen in the formula, which means that I have to change my oxygen count. Now, oxygen does not appear in just one place in the products of this chemical reaction. It appears in water, but it also appears in carbon dioxide. So rather than multiplying it by 2, which is not correct, not what's actually happening here, I'm just going to cross this out and do a recount. I now have 2 oxygens from the water and 2 oxygens from the carbon dioxide, giving me a total count of 4. Okay, so now to balance this out, well, now I have 4 oxygens on the product side. That means I need to add more to the reactant side in order to make this obey law of conservation. But luckily, 2 and 4 are both even numbers, and they've got a least common multiple of 4. So again, how can I make this 2 equal the number that I want, 4, multiplied by 2? And since oxygen only shows up in one side of the reaction equation, that means this coefficient of 2 can immediately go up and get plugged in right here. Now, since oxygen is in its elemental form, it's not bonded to anything else, changing that coefficient doesn't affect anything else in the reaction, which means my final balanced chemical equation is 1 methane plus 2 oxygens is going to yield 1 carbon dioxide and 2 waters, which is exactly what we got with the particulate diagram method. So, whichever method you prefer, go ahead and use it. You should be able to do both of them. But what happens when your reactions get a little bit more complicated? It's a little bit harder for you to use the particulate diagram method because it just takes a lot of time to write out all those particles. So here's another example in which you definitely are going to want to make use of the table of values method, and that's especially when you have polyatomic ions present. So, according to the first step that I showed you back here for the table of values method, you would start by writing each individual element you have present in the reaction under your arrow to make yourself a table of values. However, you can use a little bit of a cheat trick here. If you see a polyatomic ion present in your reaction equation, you can count it as one species. So here we have nitrate, NO3, and it shows up as nitrate, NO3, on both sides of the reaction equation, which means instead of in my table of values writing N and O separately, I can write it as one species, NO3, the polyatomic ion. That's going to help a lot when you're going through and doing your counts, because rather than having to balance nitrogen and oxygen separately, now you just got to balance the nitrates, which is going to make your life a whole lot easier. So let's go through and do the next step, our initial counts. For calcium on the reactant side, I have 1 of them. I have 2 nitrates on the reactant side, thanks to that little subscript there. And I have 1 lithium. On the product side, I have 1 calcium, I have 1 nitrate, and I have 1 lithium. So it looks like currently the only thing that's not balanced are my nitrates. So again, I can't manipulate the actual chemical formulas because that would be changing the identity of the chemical. What I can manipulate are my coefficients. So I take a look at 2 and 1. 2 is the least common multiple between them. So what number can I multiply by 1 to get the number 2 that I want? Well, I can multiply it by 2. So that means that's going to become my coefficient in the nitrogen-containing compound on the product side. So that's going to go right there. And when I do that, it not only changes how many nitrates I have, but it also changes how many lithiums I have since lithium's bonded to the nitrate. So I also need to multiply this by 2. When I do that, now my lithiums are unbalanced. So between 2 and 1, my least common multiple is 2. So what number can I multiply by 1 to get 2? 2. So I find the thing that contains lithium, just in its elemental form, lovely for me. That means I put a coefficient of 2 right there because that's what I multiplied by. And now everything is exactly the same, easy peasy. And that is your quick guide on how to balance chemical reactions.